So, okay, yeah, I'm continuing now with the lattices, so it's basically one of the building blocks of Hamiltonians, which will be shown. So, as I said, the lattices and then also the hopping, the interaction, and the observables. Then we have all the building blocks to build our own Hamiltonians. And yeah, the lattices have basically the two components, the Bravais lattice and the unit cell. As we will see here, I mean, I think you're all familiar with this. So we have, for example, the honeycomb lattice, which is a triangular lattice and has two orbitals per unit cell. So it looks like this. And how this is implemented in Fortran, so in an ALF, is that we have one type lattice, which is like similar to a struct or a class, if you are familiar with C or C++. And it is defined by 4 T2 vectors, two-dimensional vectors. So it's a so we have the two primitive vectors, which are all familiar with Bravais lattice, and then we have two other vectors which define the periodic boundary conditions, and this then together defines a finite size lattice. And since like the L2 and L1 do not have to be parallel to A1 and A2, so tilted lattices with non-trivial topologies are also possible. And yeah, for the one-dimensional systems, we just set L2 equals to A2. And then, yeah, the lattice is just created by calling this call make lattice and giving it as argument the 4 vectors and the lattice, which will be then filled by this make lattice. Also, there's an extension to a 3-dimensional lattice in progress. Yeah, and now some basic formalities on how the Bravais lattice is implemented. So yeah, the Briand zone is defined by the reciprocal lattice vectors with these orthogonality definitions, and then we have a K-space quantization, which is defined by these lattice with these vectors that define our periodicity of our lattice. And then from this, you can define these primitive vectors of our K-space, B1 and B2. And yeah, then this is all saved in this type lattice. So there's the two unit vectors which span the real space, and the two vectors which define the periodicity and therefore the size of our lattice. And from this, the number of unit cells in our vector in our lattice, in our Bravais lattice, are defined. And you have a list and inf list. So list is a mapping from an integer that goes over all the unit cells to a linear combination of the primitive vectors to get the location of the nth unit cell, basically. And inf list is basically the inversion. So you have I1 and I2, so two integers that define a real space location in our lattice, and you can map to this number n. Like not the number n, but some number I, yeah, which is goes over all the unit cells in the lattice. And then you can also find out easily the nearest neighbors. So this is very, very handy if you like just build some square lattice or some, any hopping or so, that you can easily get the nearest neighbors with this NN list array. And there's also an IMJ array, which is if we have which we use for calculating or saving correlation functions. So if we have a location RA and RJ and the corresponding integers, then with IMJ of INJ gives the index of the difference of those two locations, which is what is most interesting in a translation invariant lattice. And list k and inflist k are basically the same as list and inflist, only in k space and in real space. And here also the reciprocal space vectors and the k quantization, which are the equivalent to L1, L2, and A1, A2 in k space. As next, there's the Fourier transformation is subroutines are defined in this way. So we have some array where the first index of the array is the index which goes over the sides, over the side index in the parallel lattice. And then you can either go from real space to k space or from k space to real space with the as defined here with this convention here. And then finally, we also have a second part to the parallel lattice, the unit cell, which is the number of orbitals, we call it. So it's the number of orbitals is the number of fermionic sites per unit cell. That's might be a bit of deviation of how other fields define orbitals, I think. But it's that's how that's orbitals. And then the coordination number is like the number of nearest neighbors.
Why is it a deviation? Why?
I just had once or twice some confusion at some point with some people which used the number of orbitals differently.
Okay.
Like for example, if you it's the number, like n orb is the number of fermions per unit cell, and then these are and then we also have the positions in the unit cell.
No, the n orb are the number of orbitals per unit cell. That means for honeycomb lattice, it's 2. The number of fermions could be 2, 3, or 1, right?
Sorry,
So it's 2. It's basically a number of px, py. I mean, the number basically counts the number of fermionic operators. The indices of the fermionic operators you have, right? Ignoring the spin index.
Ignoring the spin index.
In this case, the n orb can be manipulated to put in the spin index in some cases, but okay. It's a bit tricky, right? Okay.
But the point is basically the actual number of fermions we simulate, or the number of like the dimensionality of our problem we then have, is basically the number of unit cells in the lattice times the number of orbitals. This will be in the most cases then the dimensionality of our of the matrices, like of the Green's function. So a Green's function has usually the size n times n. And to keep track of this, we have here a convention for here in this talk I called it the fermion superindex. where basically, so we also have here a list with if list and inf list, but it's not should not be confused with the list and inf list, which is part of the Bravais lattice. So this list and inf list basically translate from the super index to the number of the unit cell number and the orbital number, and vice versa. And then to go from the unit cell number to the corresponding location in the Bravais lattice, you need then let the list which is part of the lattice, and this is like the list and inf list which are above that, basically, like which are not part of the lattice. So that's, yeah, do not confuse with let percent list and let, like this percent also, this is a Fortran style. I think I'm not aware of any other languages who use it like that. So basically this would be like in C or C++ a dot. Like if you want to access members of the lattice type, you might make it with this percent. Yeah. And yeah, then that's the convention of how the super index, basically, like the NC is here, the super index is filled and connected to the unit cell index and the orbital index. Yeah. And now finally just some concrete examples of lattices that are actually also predefined. So you just you don't have to rewrite the code for that in Fortran in ALF. You just can use the module predefined lattices. And then you have, for example, predefined a square, honeycomb, n-leg ladder, a bilayer square, and a bilayer honeycomb lattice. And then they produce our lattice, the like a Bravais lattice, the unit cell, the list, the inf list, and yeah, and you just have say which lattice type, like, yeah, one of these, and then the size of the lattice. Yeah, here's, for example, the honeycomb lattice I showed before. Like it's the same as I showed before, only now written in Fortran. And then you just define these 4 vectors, put them in the make lattice subroutine, and define the orbital's position in the unit cell type, like this. Similar is if you want to write with open boundary, work with open boundary conditions, so that we have only periodic boundary conditions in one direction. Here, for example, the n-leg ladder, which is like a square, like in x direction, L1 sides, and in y direction, L2 sides. But in terms of ALF or in terms of Bravais lattice, it's a one-dimensional system, because you only have the periodic, like the translation invariants in x direction, and therefore all the sides in y direction live in the same unit cell. So they all are then, like, the structure of these 3 sides are then all saved in this let unit, because they all live in one unit cell. And this is basically just, in terms of the Bravais lattice, this is just a one-dimensional object. Yeah. And yeah, that's basically is. So here's just only another overview of our predefined lattices. Here, square lattice on a bilayer, the n-leg ladder, honeycomb, und bilayer honeycomb. Yeah.
Questions? So as what Jonas was saying is that we have a branch. I think Emily's part of to do a 3D, right? I think there are more and more 3D applications. And so it will be nice that will come in for this Yes, please. Go ahead.
So just regarding two-dimensional lattices, so as we know that there are only 5 Bravais lattices, right?
Yeah.
And then would it be possible like to have a kind of code which you can just, which combines 5 Bravais lattices in some more complicated lattices? Like, for example, honeycomb lattice is just a combination of 2 Bravais lattices, right?
Yeah.
Then you can also say, you can think about Lieb lattice, which is a combination of 3 lattices. So do you have kind of library with, which can be used to construct more complicated lattices out of 5 Bravais lattices?
No, we don't have that. But the Lieb lattice, one of the Lieb lattice would be a square lattice with 3 orbitals per unit cell. So this is, you call this 3 Bravais lattices?
Yes.
I call this 1 Bravais lattices with 3 orbitals per unit cell.
Okay.
I think it's a different terminology,
Okay.
right? So because there's different the unit cell defines the translation symmetry, right? So when you say honeycomb, triangular, so the backbone is called triangular lattice, but with 2 orbitals per unit cell.
Yeah.
So we have these n orb, which is important, right?
Okay.
So I think and then there are infinite numbers, right? There's not only enough because then so that's what you're saying, right?
Yeah,
because you have
you have 5 lattices out of which you can
So here we have, so for example, the bilayer honeycomb for you would be 1, 2, 3, 4 triangular lattices. Right. And so you say I have 4 triangular lattices and I'm placing, you could do that. Just that doesn't define the Fourier transform. To define the Fourier transform, you need 1 reference unit. I mean, that's the key point. The lattice is there to define the Fourier transform, and then you cannot combine, you cannot say that you cannot define your Fourier transform on the honeycomb lattice by saying the honeycomb lattice is just 2 triangular lattices. Then you have a bit of a mismatch.
I think that's
sorry. I'm taking too much time.
Just
Everybody's scared, huh? Oh, I mean,
I mean, the other information that would be missing if you define the Lieb lattice as 3 square lattices is the actual connectivity. Which sides are nearest neighbors, and this is important if you define the hopping term. Yeah, so that's why the strategy here is more like Vakia said, to use translation symmetries also for Fourier transformations and so on. And then the orbital structures where you encode the connectivity for the hopping matrix.
Yeah, that's a part I could have stressed a bit more, that really this the Fourier transformation and that we use the Fourier transformation is really an integral tile of how the observables are constructed. But in principle, you could overwrite this all, but then it will be a bit more headache to keep track of things. Yeah.
The use of the use of the Bravais lattice is important when we want to use translational symmetry and so on for computing the observables, right? But in principle, I could just use some lattice, and according how I define my hopping matrix to the topology I want to have, basically, then
the problem is that you're correct. You could forget about the lattice and just define just a graph.
Yes.
Right. The problem is then that when you measure correlation functions, especially time displaced correlation functions, you will fill up your disk. Because you will you know this very well. Because when I measure 2-point correlation functions on a lattice, I use translation symmetry. So I compactify the data set with that. If I don't have translation symmetry, I don't know what to do, and I write everything out, and then you have to have a big file, a big disk. I'm sorry. Yeah, there's another thing which is up, and there's a branch which I haven't finished yet, which is looking at the did you write where the positions of the orbitals were?
Yeah.
So we have in principle in the ALF we have the orbit the fundamental Bravais lattice, not the 3, just the fundamental. And then the position of the orbital, with respect to this fundamental thing. And then you can have Fourier transforms in the first Brillouin zone, second Brillouin zone, etc. And then to get, you need that when you want to link to experiments. So that's up in progress, but that'll be up and running. It's done already, but it's not deep.
Yeah, extended zone screen. There's a pending merge request there for this, I guess.
Yeah, so so you have to put in the positions of your orbitals also.
Yeah.
You have to, so you have all the information principle in this class. More questions, comments? Yes, here it is.
So I have a naive question. So for example, say you choose the bilayer model and then you decide to turn one of the interaction off.
Yeah.
So does the code from the beginning just eliminate that part of the Hamiltonian, or
No.
it has to, because I'm thinking the way, because that way you could the computational complexity could be reduced if one of it is not included right from the beginning. Going to split it U equals to 0 at some point later in the code.
There are some things like that, but I think it's not as efficient as if you just leave the part explicitly away. Like if you put some interaction to 0.
I think there are some ifs somewhere. Johannes, you maybe have that.
Yeah. So I'm actually not 100% sure what the latest status is, but at least at some point there was the idea that when you have an interaction vertex and the coupling constant of that vertex is 0, then you know that like everything is an identity. You will accept or reject all the spin flips because they have the same weight, they don't matter. So there were ideas of having quick returns in some places, but this was then at other times also problematic because maybe the update for the fermion doesn't matter, but with S0 you encoded some internal dynamics where you still have to sample them properly. The other thing is also that now it depends a little bit on how much you want to decouple them. If you remove the second layer completely, then go to the single layer version. If you still have hopping between them, like fermion hopping between the two layers, then when you calculate the fermion determinant that gives the weight of the update, you have to include both layers. And the matrix that we work with in these B matrices is a matrix in the number of fermionic degrees of freedom.
Yeah. So I guess that
you have less vertices, so the number of field updates that you have to do are less. But each time you update, in principle, you have to account for all fermions because they do hop.
So if you declare to repeat, if you declare a bilayer model and you put one layer to 0, the code may not realize that it's a single layer model.
No, the code won't.
Will not.
No.
However, if you keep your you have a bilayer model and you put one U, for example, on one layer to 2 and on the lower layer to 0, then the code may notice it. We have to go back in the code and would not allocate the space you need for the interaction vertices on the second layer. If that doesn't happen, it's very quick to repair this. Right? Okay, I think that could be. Comments, questions? Okay.
Perhaps one more question.
Yes, please.
If you have a one-dimensional system along the A1 direction, A1 primitive vector, you always have periodic boundary condition, or you can choose open boundary condition?
Open boundary condition, basically in the context of how we do it, means that you don't have a Bravais lattice. Like open boundary condition, like the Bravais lattice implies that you have a.
Can you go back to the end?
Can you go back to the slide?
Yeah. I see. That's why I asked. So
if you want open boundary conditions for the end leg ladder in one dimension, you define an end leg ladder, right? But with a length of the leg 1. Because a ladder, by definition, that would be it. Do you see the slides? Do you see me in the slide?
Yes, yeah, yes.
So this is
Yeah.
1, 2, 3. If I take A1 equals.
No. Maxime, can you adjust the camera?
I'm sorry.
Just turn it a bit to
I mean, if you can you go to the end to the summary slide? To the
Yeah.
summary slide, you
Ah,
have
yeah,
the
sorry.
ladders. I know that we have one example of that
sorry.
because when testing HMCI, so this one, the C, right? Can you see me? Yeah, here it is. So this would be if you take this for the end leg ladder, which is the C, you have periodic boundary conditions in A1, but open boundary conditions in the Y direction, right?
Yes.
So if you
Yes.
want to have if you want to quickly get an open boundary, three model with three, you just put L1 equals 1, and that will give you what you desire.
And just to be on the safe side, it might also be a good idea to turn the hopping between like what's currently the X direction in the A1 direction. Turn this hopping off, because with periodic boundary conditions, this could turn into a chemical potential. But the hopping connects back to
But
itself.
I think there's a test for that.
Okay.
Because we use this for output. If you look at we have one test for the HMC and for the Langevin, and we wanted to get rid of zeros of the determinant because of known issues. And that was exactly what we used. And there's a Python script for that.
Yeah.
So I think that's turned off. Otherwise, we would have issues, I think.
Yeah.
That's ticked. There are many problems with the lattices. I mean, the pitfall, which everybody asks all the time, you want to have a 2x2 Hubbard, right? And then, of course, you say 2x2 square lattice, and then you have the hopping, which is counted twice. And then you say the code has a bug. Doesn't, just that you have a factor too.
Well,
I don't know. All these things you could test all the time, which we don't.
Depends on how you define the 2x2.
Yeah, I know. That's a problem. Yeah. So a 2x2 lattice would be a ring of 4. You have to define like this, etc. You have to be careful, right?
Thank you.
Wait a minute. I'm sorry. Thank you. I'm sorry. We've continued on your question. Here you go, Pi.
No problem. That
It's
was enough.
okay.
Thank you.
I'm sorry. We're trying to. Okay, good. Thanks you for the question. More questions, comments? The advantage of being online is that you're not as hot as in here, right? I hope that you guys have air conditioning. We don't. Our air conditioning is not working. So yeah, go
I
back.
have a little question about the structure of the ALF. So if I only want to use the global tau move, so I should modify the code. Am I right? I think that it's always a single flip.
I think
No, there's no modification to it.
So, but can you turn single spin flips off? Yes,
Yes, you can.
Yes,
Yes.
you can turn the single spin flips off, and then only do global tau moves where you are allowed to change an arbitrary number of auxiliary fields on a given time slice.
So there's the
So that the cluster has to be on the same time, but you can do arbitrarily many of them.
there are two variables: sequential start, sequential end, right? If the sequential start, and sequential end at the end, I think this is the name of these variables. If you check them,
There's some if to tell that the sequence is
yeah, we can discuss it. There's a lot of fiddling around. I agree, but it does. You don't have to change anything in the code, apart from the Hamiltonian. But there is fiddling around with that. I agree. Other questions?
May I ask why you are interested in these kinds of moves? No, this is an honest question. Why do you want to do why do you not want to do single spin flips on a time slice, but some other time update?
looking for something?
because I just want to add the U1 gauge.
Yeah.
You know
All the
that.
gauge- So there is one.
So I must use the global tau to.
There is
I'll
one
have
problem
to
in the
do
structure of the
the
ALF which we have to repair, and
field.
that's gauge theories, right? I don't know how to write on the blackboard without a pen.
Yeah. Has someone seen the pen for the
Does someone take
whiteboard?
the pen?
Attempt to steal things.
Anyway,
Kleptomaniac.
if you want to write an SU2 gauge theory or U1 gauge theory, Z2 would work.
Shouldn't be, no.
Then it's a bit of an issue for the ALF, and you have to split your field into a real part and an imaginary part, right? So I'm sorry. So you see, let's say that you have a you have a U1 gauge theory, A on the bond, Aij C of J plus Hermitian conjugate. That would be a bond, right? That would be a bond. And A is a dynamical variable now. So this does not fit as a that does not fit as an interaction vertex. The interaction vertices you have to split this, so you would be e to the minus delta tau. You will have to split this into two interaction vertices, one with a cosine and one with an I sign, which couples to the current. And that's where you need it, because you have two, now you have two vertices which couple to the same field. One is the cosine and one is the sine.
And they're tied together.
And they're tied together, right? So we have to, so for the people who are interested in lattice gauge theories, and there are many solid state physicists who are getting more and more interested in lattice gauge theories, then we have to, the goal would be to have a thing with a generic matrix here, and to be able to have some type of way of doing this. That would be much more efficient. So we have a workaround for the moment, but it's not very nice.
So the underlying argument is that at the core, when we designed ALF, we had one field for one operator, fermion operator that it couples to.
We always had the structure of E to the a field. So let me call it generically F times an operator, and this operator had to be Hermitian.
But there was one operator for one field.
And
this is something that you would have to break up, because now you have the same field coupling to
exactly.
two operators, the real part and the imaginary part.
So we have to update the things to be able to cope with U1. Z2 is okay because that's a real number, so you don't care. You can just put it in front, right? For phonons, it's okay. But if you want to have a generic thing, that doesn't work. So that's a caveat which we did not think of. That's why GalPi needs.
I also have I'm not sure whether this is a question. I think for the for example, for the honeycomb lattice, if I set L1 is equal to 9 and L2 is equal to 3, there will be a
bug.
warning.
A bug.
Yeah.
So in that case, you have to write something on Discord.
Yeah.
Or an
okay.
issue. I don't know. I never tried it. Huh?
Issue on GitHub.
Or in GitLab, right?
Yeah.
So when you have a bug, I'm sorry, of course, when all the bugs which are there, an issue on GitLab, everybody can post issues, right? It's open. That's a bit of a problem. So Discord. Or the mail. Did anybody ever have, also the online people, did anybody have issues with the fact that we have a GitLab with some restrictions and not a GitHub? Is that a problem for anybody of you? No? Sorry?
I know that you are using, I know that Evo is using ALF, so I was just looking at him and asking if he had issues in this direction.
And we got a referee comment saying that it was not good. That's why I'm asking you. Maybe that's the right. Anyways, so you post when you have these problems, just feedback, right? That's the idea of a community, and then we don't do this all full time, so we try to do our best to make it work. But, okay, so online people are also satisfied with the answers and questions.